So the simple pendulum, we can analyze some bits about it using conservation of energy. And we can also approximate it as an isolated system. So for a pendulum, generally what we're going to be looking at is two parts. We're going to be looking at the highest point of the swing, and we're also going to be looking at the lowest point of the swing. So the lowest point of the swing is going to have the smallest amount of potential energy, but it's going to have the greatest amount of kinetic energy. What we're going to do to simplify our life at this point, though, is at the lowest point of the swing, usually what we do is we set that as our reference height to be 0. What that allows us to do is at the minimum or at the bottom of the swing, with the height being 0, that allows us to set the potential energy to 0 at the lowest part of the swing, which means our mechanical energy's contribution is due to the kinetic energy, or the maximum kinetic energy. And then when we're at maximum height, we know that we're going to have maximum potential energy, because this is where we're going to have minimum kinetic energy, or we're going to have 0 kinetic energy just because we're at maximum height. So what we can do is we can sort of expand out our statement for conservation of energy. So we have this piece for the top of the swing. We also have this piece for the bottom of the swing. So at the top of the swing, we have this EK top plus EP top. And then when we get to the bottom, we have this EK bottom plus EP bottom. Now, as we said, we're going to simplify our analysis a little bit. At the top, we know the kinetic energy should be 0 because it's not moving. It's at maximum height. So we're going to set that to be equal to 0 for our simplifications. So we're going to set this term to 0. And at the bottom, we're going to set that as a height of 0. So what we're going to do is we're going to set EP bottom to be 0. What that's going to allow us to do is that's going to allow us to write this statement like this. We have this E potential at the top is equal to EK at the bottom. Now, in Science 10, you've probably seen this written as EP max equals EK max, or the maximum potential energy is equal to the maximum kinetic energy. The big thing you don't want to write, and I see students write this all the time, they just write EP equals EK. Oh, I don't have a red pen, but this is going to have to do well. That is very, 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 very wrong. EP is not equal to EK. The max words are very important here. The maximum potential energy is going to equal the maximum kinetic energy, because at these particular points, the maximum potential energy is equal to the mechanical energy at this point. At this point, the maximum kinetic energy is equal to the mechanical energy. So we still have a statement that mechanical energy is conserved, but we have to be really careful. So if you're ever confused with the pendulum, write out your statement of conservation of energy. Don't just write EP equals EK. That is going to get you absolutely nowhere, and it's unbelievably wrong. So let's look at an example with a pendulum. So we have a pendulum bob. It's got a mass of 250 grams, so we're going to have to deal with that. So we want that to be in kilograms. It's suspended on a string that's 2 meters long. So the bob swings through. Its lowest point is 5 centimeters above the floor, and its highest point is 25 centimeters above the floor. So we want to find the mechanical energy relative to the floor, kinetic energy 15 centimeters above the floor, and finally speed 15 centimeters above the floor. So this question is very guided. It's kind of trying to take you through all the motions of this. So let's look at what's going on. So we have a pendulum. So I'm going to draw my little roof here, or ceiling. So we have a pendulum. You know, it's got a length here. It's going to start here, and then eventually it's going to swing its way down sometime later to this point here. Now, what we have been told in this question is that we are told at the lowest point we're 5 centimeters above the ground, and at the highest point we're 25 centimeters above the ground. Obviously, I shouldn't have to write this, but this is definitely not to scale. Now, what we would like to find is we'd like to find the mechanical energy of the bob relative to the floor. So this is going to require, and the relative to the floor is the important part. So the mechanical energy, as we know, is the kinetic energy plus the potential energy. Now, I can find the potential energy at either of these points because I know how high they are above the ground. But the kinetic energy, I have my arms tied up a little bit. The only place right now I know the kinetic energy is at the maximum height, because at the maximum height we know that V is going to be equal to 0. So we know EK equals 0 at max height. So what I'm going to do is I'm going to calculate the mechanical energy at the maximum height, and that's fine. Wherever I calculate the mechanical energy, it will always be a constant. So at maximum height, we're going to use the mass times g times this height above the ground. So we have our mass of 0.250 kilograms. We have our 9.81 meters per second squared. And then our height above the ground is 25 centimeters, or 0.250 meters. So this is going to give us the mechanical energy at this point, which we're assuming this is an isolated system. This is going to be the mechanical energy of, the mechanical energy everywhere. So I'm writing out all these sig digs, and then I could say that the mechanical energy of this is about 0.613 joules. So to emphasize again with conservation of energy, this does not change. This is a constant. So we want to make sure that we respect that. Now, if I knew the speed at the lowest point, I should get the same number. But we don't know that, so we're just using the max height. So now we're interested in finding the kinetic energy 15 centimeters above the floor. Well, we know mechanical energy is not going to change. So we know that mechanical energy is just going to be the kinetic plus the potential. So if I would like to find the kinetic energy, I'm going to take the mechanical energy, and I'm going to subtract off the contribution of the potential energy at this point 15 centimeters above the floor. So we're going to minus mass times g times that 0.0150 meters. So our mechanical energy, that does not change, minus that mass of 0.250 kilos, 9.81 meters per second squared, and then this time our height of 15 centimeters, or 0.150 meters. We're going to take that off. So then I'm going to get about 0.24525. I'm writing out all the extra sig digs just because I need those in the next part, so I want to preserve as many digits as possible. So at this point, 15 centimeters above the floor, we can say that the kinetic energy is about 0.245 joules. And then the last part, it wants the speed at 15 centimeters above the floor. Well, we know the relationship between speed and kinetic energy is EK equals half mv squared, or the speed is twice the kinetic energy divided by the mass, and then we're going to square root all that. We've seen this rearrangement quite a bit, so I'm not going to go through all the details again. So at 15 centimeters above the floor, we found the potential energy in part B. We're told the mass of this bob is 0.250 kilograms. So the last thing we're going to do is we're just going to calculate that. I'm going to take my square roots, and I'm going to get about 1.40 meters per second. So when this pendulum bob is 15 centimeters above the floor, it's going to be traveling at a speed of 1.40 meters per second. So the pendulum, it's no different in its application of conservation of energy. We just have some simplifications we can make to it to make our life a little bit easier. So we haven't changed anything with conservation of energy. We've just made a little bit of tweaks to the equations to make our life a little bit easier.